So that covers the subject of chemistry. Let's now look at a completely different subject. Completely different subject. And the subject is epidemiology, which is the study of the spread of infectious diseases through a population. So these are going to be population dynamics models. And the two critical quantities, the two critical state variables are going to be S, which is going to stand for the number of susceptibles, that is, people who are capable of being infected but are not currently. And the second key state variable is the second key population, which is the number of infecteds. Now, in a model like that, as we start to write the S prime and the I prime terms, let's ask ourselves, what makes S go up? What makes S go down? So, what makes S go up? Well, clearly, maybe some kind of birth rate of the S's. Possibly an immigration term. Those are the only major pluses that I can think of right now. And then the big question is, what makes S go down? What makes the number of susceptibles go down? And the answer is an event whereby a susceptible bumps into an infected. And the precise definition of bumps into varies from disease to disease. In the case of HIV, that means sexual contact. In the case of the flu, it means sneezing radius, getting inside the sneezing radius of. We are going to be developing the pioneering model, the first people to make this kind of model. And that would be Anderson and May in 1975, talking about AIDS and trying to understand the spread of AIDS in a population. So in this case, what makes S go down is an S bumps into an I, and with probability beta, the number of S's goes down 1 and the number of I's goes up 1. But there's a little wrinkle in this model which is different from the shark tuna, and you're beginning to see the shark tuna aspects here already. But it's slightly different in the sense that in the shark tuna model, we have the term sharks times tuna because a shark only bumps into a tuna. The sharks know who's a shark and who's a tuna. And there isn't a lot of shark, oh, excuse me, you're a shark, I thought you were a tuna. That doesn't happen. But what happens here in the epidemiology case is that other thing, namely an S bumps into an unknown. And the unknown could be another S, or it could be an I. So when we're going to do this negative term here, the S is an S, and the question then is, what is the probability that the random person that they bumped into is an I, which will be the critical act of infection? And that's just equal to the fraction of the population who is infected. So we have that. And then, of course, not every time an S bumps into an I do we get an infection of the S. That is, of course, there is a probability function there, which is called beta. And beta is the likelihood that an interaction between an S and an I infects the S, lowering it by 1, and upticking the I by 1. So that quantity is beta S I over S plus I. That's for a single encounter, in this case, a sexual encounter. But you may have more than one sex partner, and so we have to multiply that by C, which is the number of times that you roll the dice. If you roll the dice with a certain probability, and you roll the dice twice, the probability is twice as great of getting a given outcome. So we have the minus term. We can then immediately put that into the I prime equation as a plus C beta I over S plus I times S. And then we have to put some things in here. We also need to include a natural death rate for the susceptibles. So I'm going to call that per capita death rate mu. And we have a minus mu S in the S prime. And now let's finish the S prime. We're going to forget about immigration. We're going to consider a closed society here. And because they were looking at a short-term influx, Anderson and May did not have a population-dependent birth rate, because that's something that comes online 18 years later. They just called that a constant, and they called it little b. So now we have S prime equals b minus C beta S times I over S plus I minus mu S. I prime is equal to all the susceptibles who got infected. They are also going to have a natural death rate. And by natural death rate, I mean auto accidents and heart attacks and whatever. So that's going to be minus mu I. And then we also have to allow for an I-dependent death rate, in which infected people suffer higher death rates as a result of their infection over and above the mu term that we all suffer. They're also going to have another death rate. I'm going to call it mu sub I times I. This is the special infected particular death rate. And then, because this is an HIV to AIDS model, the I just represents being infected, that is what we would now call HIV positive. What then happens, and we need a third variable to represent this, is the variable A, which stands for the symptomatic condition, which is called AIDS. And that A prime is going to have a certain, the positive contribution to A is going to be people graduating, as it were, from I into A. That is the non-symptomatic but positive becoming symptomatic. And what is that rate going to be? We're going to call it nu, the Greek lowercase nu. So this now gets another nu I. And these are people leaving I for A at a rate nu. So A prime is clearly going to be nu. There's the positive term of the nu I minus the natural death rate minus an AIDS-specific death rate, which I'm going to call mu sub A times A. And there is the Anderson-May model for the epidemiologic spread of HIV in a population. So let's stare at this term that's the key susceptible meets infected, the shark meets tuna term. And we said it was C times beta times S times I over S plus I. C is the number of sex partners per unit time. Beta is the probability that a sexual encounter results in infection. And of course, this is the shark meets unknown probability term. So if this is the key term that is creating the infection, we stare at these terms and we realize how critical these two parameters are, C and beta. And since they appear as their product, it's kind of interchangeable. You could lower one, or you could lower the other, or you could lower both. But what you should not do is lower one and raise the other, because that's going to cancel out. So C, we understand, it's the number of sex partners. It's the number of times you roll the dice. And beta is the likelihood that a sexual encounter results in infection. So there is a critical choke point and a key variable to operate on to change the outcome of the model, to change the result that will eventuate. How can we raise or lower beta? And in particular, we're interested in, obviously, in lowering beta. Well, for example, safe sex practices. Use of a condom lowers beta, lowers the probability that the encounter results in infection. So certainly safe sex practices. So safe sex implies lowering beta. But drug therapies for HIV, AZT, for example, a lot of drugs against HIV prevent the HIV virus particle from incorporating itself into the host cell. And what is the value of that? Answer, you're lowering beta. This time you're lowering the ability of the virus to infiltrate the cell. That's another case of lowering beta. And then even with the very simple 3-variable Anderson-May model, you can do an exercise, very straightforward, where you ask, how much do I have to lower beta? If my default parameter values give me an infected as a function of time, and it goes like that, that's not so good. And the question is, if I lower beta a little bit, what does that do? And the interesting answer is you don't know. You don't know until you run this model, until you simulate this model, how much of a change in beta. If I have beta, what does that do to the outcome? Does it make the outcome half as large? No, you have no idea. If you halved beta, it might have no effect. It might also have a completely successful effect of eradicating the epidemic altogether. But the same thing is true of a 20% reduction in beta. It might be more than enough. It might be not nearly enough. These are nonlinear models. Look at that S times I. These are nonlinear models, and so arguments based upon linear proportionality don't work. So the answer is, and you can only find this by simulation and by what we call numerical experiment, that is experiment in the computer, we need to find how much do we have to lower beta to make that infection look like that, make the course of infection over time look like that. And that is a question that depends essentially upon what disease you're trying to model and what the terms are, and especially what these parameter values are. So that's a very simple 3-variable, almost a cartoon, almost a caricature, but still effective in making some basic predictions. But it's fairly simple. And you might want to ask the question, is this really being used? And what does the research frontier look like? How far is the research frontier from this 3-variable Anderson-May model? And the answer is it's not that far. So here is a paper that came out a couple of years ago from the CDC, from the Centers for Disease Control. MMWR is the Mortality and Morbidity Weekly Report. It is the CDC's weekly report to the president on the state of the nation's health and possible danger things to look out for. So in dealing with the Ebola outbreak in Africa, what was that, 6-7 years ago, they were obviously very concerned with the course of the epidemic. And there's a lot of different things you can do to try to stop the epidemic. You can try quarantining people. You can try giving drugs to abate the symptoms. You can try giving drugs to cure the disease. You can try a lot of different things. And the question is, what is going to work? And the CDC, being who they are, put together a pretty stellar team here. You see the MDs and the MPHs and the PhDs. And they put together a model. And as you see, they say, to aid in planning for additional disease control efforts, CDC constructed a modeling tool called Ebola response. So what is Ebola response? This is Ebola response. It's an SEIHFR model. Now, the style of modeling that we're using here used to be called SIR, for susceptible, infected, recovered. In the case of Anderson-May, there was no recovery, and so it was an SIA for susceptible, infected, AIDS symptomatic. Here is an SEIHFR model standing for susceptible, exposed, which in the case of Ebola is not quite the same thing as infected. So we have susceptible, exposed, infected. The H stands for hospitalized, because that's a category, and some of the infecteds get hospitalized and some of the infecteds do not get hospitalized, and they're going to give rise to different dynamics. F stands for funeralized, because once again, the people who die of the disease, some of them receive funerals and some of them do not. And at the funeral itself is a mechanism for the spread of Ebola. And so we have to have a separate category called funeralized. And then, of course, in this disease, you can recover, so there is an R variable. And you see the arrows going from the one categories to the other. So this is a 6-variable model as opposed to the 3-variable Anderson-May model. But this is the research frontier. This is pretty serious. This is folks from the CDC working together with folks in Africa to try to combat a deadly epidemic. So you see that they're using the same kind of modeling, and then they do a very simple experiment. They're trying many, many different combinations. What if we can get anti-Ebola vaccine into 20% of the population, 30% of the population, 50% of the population, 80% of the population, 99% of the population? Which of those is the magic percentage? Answer, you have no idea. You've got to run the model. You've got to get the parameter values correct, and then you have to run the model and try those different scenarios. So they had available to them a certain amount of drugs, and then a certain amount of flexibility in terms of their protocols of treatment, especially getting the Ebola positive patient out of their immediate community surrounding and into a quarantine unit where they're not going to be spreading it to other people. And there again, so your policy of getting people into quarantine. How many people? 20% of people, of infected people? 60%, 80%? Varying scenarios. How long will it take you to do that? Well, I can do 30% in 2 weeks. I can do 60% in 5 weeks. Okay? That all goes into the model. And the result is very interesting. What you see at the top is what the model predicts with no intervention. And you see that very unpleasant exponential rise of the number of cases. The two different lines are because you have to correct for underreporting of cases. The actual number of cases is going to be larger than the number of reported cases. So the dotted line is the actual cases, and the solid line is the reported cases. But both of them are terrible, and you see them going up to gigantic numbers. Then they tried an intervention. Well, actually, they tried millions of interventions, and a lot of them didn't work, and this one did. By diddling all of those parameters, they came up with a strategy that was something like, okay, we need to get 60% of the infecteds into a quarantine unit within a week, and then we need to treat the remaining people with this much efficacy in that much time, and do these other remedies with that much efficacy in this much time. And when we plugged those into the model, you see that the growth of the infected saturates. And if you notice those numbers on the left-hand axis, they saturate at a much lower number. So the lower tracings represent a successful strategy against Ebola as deduced from the model. So imagine yourself now, 10 years from now, being in the field somewhere, and the question is, how much vaccine have we got and how much damage can we do with it? And you say, I don't know, let's figure it out. And you whip open your laptop and you start plugging numbers into a model, and you can actually make serious predictions about how effective do we have to be in order to kill this epidemic.